Okay, I'd like to welcome everyone to Denbigh Amateur Radio Club and to our latest club meeting. A very big welcome to our club members and a welcome to visitors to the club. And indeed, we've got at least one person who spoke at the club just a few weeks ago, Wayne from Mission in Texas, who's popped up as a visitor interested in the subject matter of our discussion tonight. So everyone's welcome. We keep saying that. If you've discovered Denbigh Radio Club meeting by one of our postings somewhere, you're always welcome to attend. You don't have to join the club, you don't have to pay us any member, and you can participate the same as everyone else, and we're delighted to see you. We're just trying to promote and sell the hobby of amateur radio, and we've been trying our very best over the last 2 years to cover virtually every aspect of amateur radio, whether that's moon bounce, whether that's contesting, whether that's DXing, whether that's building radios, everything. We've tried to cover every aspect of the hobby. I'm sure there's bits we've missed out because it's that kind of hobby. So tonight I'm very, very pleased to welcome Jim Bacon, G3YLA, to the club. Jim is an active member of the Norfolk Amateur Radio Club, I think, Jim, and was and is, I guess, just because you practice as one doesn't mean you're still not a professional meteorologist, as well as a long-standing radio ham. So Jim, I'm going to hand the microphone over to you and introduce a subject dear to our own hearts in Britain and in the radio ham community, the subject of weather that we all love talking about and propagation that we all love talking about. Jim, over to you.
Thanks very much. Well, it really is nice to see so many people here, and what a great international crowd. I think it's fantastic. So it's one of the strengths of these online sessions that we've got used to over the last 2 or 3 years. I have to say there's pluses and minuses about it all, but overall the ability to join in with distant groups and to see and hear talks from places where you wouldn't normally have access to them, I think is a great asset, and we're going to miss this if we all go back to just meeting at clubs. But when we can get these things going, it really is great, because the one thing for me, from my side of this, I've done a lot of talks over the years about weather and radio, and the great thing for me is that it gets me out and interacting with people, so I find out what really triggers you about the two subjects that are dear to my interests. So it's a great way of communicating, and this is one of those things which fits all the bills and ticks the boxes. So just to set out some ground rules here, I'm going to talk about some recent work I've been doing, because that's the bit that's of most interest at the moment, and this year is going to be really, I think, significant in terms of revealing one or two of the things which have been kind of tinkered with over the years, and I've now got to a position where I think we can validate some of them and probably chuck out a few as well, which is the sad thing about doing more rigorous verification work. You suddenly find out what's not working. Anyhow, okay, so what I'm going to do is do a talk, but I don't really mind if somebody's got a really pressing need to ask a question, then probably shout out. But unless the club has a strict rule about not shouting out, then I'm happy to leave it all to the end. But that means we're then going to have to click backwards and forwards. So let's see how it goes. But don't worry if we have to pause and deal with a question. I'm going to attempt to share my screen now. So let's see how this works. I'm going to share the screen, so that's that, and that's that, and we'll do this bit, and we should see that. You should see a fine picture of a B1 on there.
We can indeed.
Yep, good. Right. If anybody's really on the ball, they'll know that was Cambridge Shed before they built the bus station on it. So let's just do this. Why is that not doing something? Come on, you can do it. Denbigh, here we go. Is that going to do it? There it is. Right. Okay, and if I do this, are we all seeing that full screen? Hopefully we are. Good. Okay, off we go. Right. This is basically a result of my tinkering around over the last sort of 12 months or so with getting direct access to ionoson data, but via the very good system that registers the data from the individual ionosons and makes them available via a database in the States. And it's a fantastic resource. And I've been working with data from them for a long while, and it's absolutely top dollar. And the other bit of this, which I'm really hugely dependent upon, there are two other bits. One is programming support from a colleague of mine at work who's made the PropQuest video possible, and that website is really a result of his taking pity on my programming efforts a few years back. And since then, I've been so embarrassed by my lack of programming skills since I stopped doing it professionally many years ago. I've been dabbling with Python and Matplotlib and SQL and things, and been doing some other work with coding, which has involved deconstructing the raw ionoson data to help it fit in with some of my work on Sporadic E. So this is kind of as a result of that. And it's important in the sense that it enables me in real time to fairly quickly come up with analyses of what I think might be, or what might be going on to the weather ionosphere link on a given day, and not have to wait for ages and ages to get under the bonnet and see what's really happening. So this is going to be explaining why I've done what I've done there. The other thing which I have to say a big gratitude for, a big thank you, is to you folk out there who are hugely enthusiastic in Sporadic E matters and who take time to submit your logs, because a lot of this is triggered by me being a weather forecaster is kind of something which means people are entitled to come up and jab you in the street and say, "Oi, what about this rain yesterday?" And so you get used to that. But it also means that people do communicate with you about things that may not or have gone particularly to their liking. And when it comes to Sporadic E and radio, for many years I'd go around the RSGB convention and I'd be attacked from all quarters about is it to do with this, is it to do with that, and so on. And I thought, well, really, it's such an interesting subject, we should try and find out more. So the fact that you folk put your logs up there on the various clusters and things is really important, because that's what triggers me into looking at things. Right, onwards and upwards. So this is kind of a way of building in a bit of an excuse at the beginning about a talk such as this, which you can't really explain everything that describes Sporadic E, even if we knew everything, and I certainly don't. But there's a lot in there that's involved. So this is a schematic I produced many years ago now, and it seems to be standing the test of time in the sense that it makes it simpler for me to understand which bit of the problem I'm dealing with. Now, the idea of Sporadic E up at the top of the bit that we're interested in here, this is at a height of about 110, 120 kilometers above the ground. So it's a long way up there and way above the weather. And the weather bit here tends to finish at about 10, 12 kilometers or so, depending on where you are. So there's a big gap between the two. And there's a lot of work going on about how atmospheric gravity waves, this is what AGW are, they're wave motions that have gravity as a restoring force, but it's essentially a perturbation that comes from lower down that can ripple up through the atmosphere and reach the ionosphere. And it's here that it produces wind shear, which is a change in the wind regime, a change in wind direction, or a change in wind speed, or both, is termed wind shear. So any variation in that has an impact on things that go on to produce Sporadic E. Now, one of the things that goes very largely hand in glove with Sporadic E is Meteor input, because when many decades ago now they launched some rockets, luckily through Sporadic E layers, they discovered that the composition of them was ionization from meteors as they burn up. So that's the interest with meteors, and that's really why, for as long as folklore about sporadic E has existed in amateur radio circles, everybody always looks for meteor showers and books some leave and tries to work sporadic E. It turns out that it's far more important what the background meteor content is. Because meteors are coming in random meteors all the time, and that varies through the year. It varies from year to year as well, and varies quite extremely from day to day. So there's a whole bunch of stuff going on up there that changes and makes this a very fickle beast. But what's come out is that the meteor input is a crucial factor in all this. So we'll be tinkering about with loads of other things, and if we aren't aware that this thing up here in the top left is important, then we may come to some rather dubious conclusions. What actually happens is that the changing winds have the effect of moving ionized particles from the meteors, the ionized elements. Mainly it's silica, magnesium, iron, things like that. And the significance of those is that they're long-lasting ions. They take a long while before they recombine. And the Earth has a magnetic field which is moderately stable most of the time, but occasionally the K index represents how disturbed it is, and if that becomes higher, then the magnetic field is all over the shop. That's not good. But when it's more sort of how shall we say, calm, then these wind shears can have an effect of converging this meteor ionization into a dense layer. And that's why the Sporadic E process has long been known as a result of development work by Whitehead and others back in the 50s or the 60s, that it's the wind shear theory of Sporadic E. It's nothing to do with wind shear down here where the weather lives. It's to do with wind shear up here where it's blowing charged particles across a magnetic field, the Earth's magnetic field. Now, these gravity waves that bring this varying wind modulate what is already up there as a wind. This thing in the top right is the semi-diurnal tidal winds in the atmosphere, and the best way I can come up with a explanation for that is that as the Earth spins on its axis, it's facing the sun, and the light is shining on that bit of the atmosphere, and it warms it, and it expands, and there are pressure differences at height, and that produces a wind regime that varies as the Earth rotates. So you get it. There are many patterns up there that are measurable, but the semi-diurnal component of this is particularly effective, and at the E region height, and that is by and large the bit that determines this double bimodal peak in Sporadic E. You get an event in the morning and another one late afternoon and evening. So anyway, a lot of stuff going on here. What this work is all about is trying to find out which, if any, of these things are important and which we should really concentrate on, and how they affect what goes on with the E region and Sporadic E. So hopefully everybody's okay there. So part one, we're going to look at some ionoson data, and we're going to see if we can actually see a Sporadic E layer descending as it forms. And then we're going to look at something called the EPI, which is a map that appears on PropQuest website, which plots where certain situations conspire to make E's perhaps more likely. And then third, a look at this is the tricky bit, verifying Sporadic E data from the ionosons against some of these weather related notions that we have about what might be helping to cause them. So there's a lot of scope for things to fall over in a heap here, because we've gone on for a long time developing rules of thumb and operating experience and so on, but as we saw with the previous diagram, there's so many other things there going on, so many other things that can affect it, that you can easily come to the wrong conclusion. Anyway, let's press on. So first bit, it's going to have a look at these tidal winds and to see if we can detect them in a routine way from the ionoson data, and see if they're able to scoop up the debris from the meteors into thin enough layers to be effective and make sporadic E. So let's start off by explaining this. I'm just going to move this little side border out of the way so I can see the diagrams. There we go. So this is a schematic version. So we've got altitude going up on the y-axis on the left from 75 kilometers at the bottom here to 150 kilometers. We've got time during the day going along the x-axis, and the idea is that meteor input comes in, and as it reaches areas of denser atmosphere, the friction and so on will cause it to ablate or ionize, and it vaporizes, and you get all these ions that are quite long lasting. And then you get sporadic E trying to form because of these wind shears that I mentioned. Now, wind shears happen because of these semi-diurnal tides. It's something that happens in the same way that the tides on the ocean happen. You know, they're going to happen, nothing to do. Sometimes we notice it, sometimes we don't. So what makes these different is that you occasionally get these gravity waves, atmospheric gravity waves, not waves of gravity, but waves whose restoring force is gravity, propagating up from something down below, which in this instance is weather. So anyway, these come in, and as this semi-diurnal tidal flow, this variation in the tides, something I have to say at the outset is that one of the functions of these semi-diurnal tidal flows, which are in themselves a class of gravity wave, one of the things is that if you stay in one place and look over time, the convergent node descends with time. It's a property of these types of waves. So this favourable bit where E's could be made is at its best where it comes up higher up and then gradually descends. Now, perhaps we can think of something that might not go quite in our favour. If it keeps coming down, something will not go well. But for the time being, this is the concept we've got to have in our mind, that sporadic E normally will be part of this descending tidal wind zone, which is good for making sporadic E. It descends with time, and something else can sometimes interfere with it, a bit like modulating an AM signal, if you like, and it will produce an even better opportunity to converge this ionization, which is there. It's floating around there from the burning up of the meteors, and it will converge it more effectively. So the place that we're interested in is a gradually descending node, and because we've called it from a couple of slides back a semi-diurnal tide, it means we get two of these, one in the morning and one in the late afternoon and evening. So the initial formation, usually we start spotting it well above 125 kilometers. It could be about 130, 140 kilometers even, but it's a bit flighty, and there are rapid changes of height then, and then as it comes down, the rate of descent decreases. But the actual frequency increases, and can be very rapid increase, till you get to what appears to be a lower height, which is around about 100 kilometers above the ground, a little bit below in some cases, but it's this area of interest that comes down and intensifies as it comes down. Now, sometimes you get a really short-lived intense patch when it's fairly high up, and for some reason things don't stay together and it dissipates quickly. So it can happen quickly and dissipate quickly when it's up here in this region. But usually once it comes down here, then it tends to be a bit more reliable, but it's at a lower height. And one thing that comes off the back of that is, of course, that lower altitude E layers are going to give you shorter path distances. So you want to be involved at the beginning if you can, but it is a bit flighty up there. Anyway, so using these two periods, we end up with what is in effect our two windows of opportunity during the day, when these descending areas of favourable conditions are in roughly the right sort of place to help us make E's given other things. So in theory, if it was just those semi-diurnal tidal winds just happening because the Earth spins on its axis and you get it going around. So a different bit of the atmosphere is heated up and so on, and you get these twice daily nodes which are of interest to us. There's nothing in that says sporadic E will happen here and not there. This is everywhere sort of type of deal. So something has to happen to make it focused on a place. And the thing that I think does play a role here is these weather generated atmospheric gravity waves that make this converging together, the wind shear bit, more effective in a very regional sense. So not across the whole of Europe even, but across a bit of it. And that focusing could be to do with a weather thing that makes these gravity waves. And you get one in the evening as well. So we get these two windows of opportunity as a rule. So you get these two semi-diurnal tides, a daytime one in red here, and a nighttime one. And there are several periods of tidal winds up there, but these are the three which we're going to focus on in this section. The diurnal tide, which varies once a day, but basically these can interact with each other. What quite often happens is that the semi-diurnal normal sporadic E type windows of opportunity come down and reinforce what's already down here, and we end up with a complex sort of combination of all these things going on. But it doesn't come much lower than that, because as you get lower in height, there are more molecules, there's more air, there's more atmosphere, so there's more chance for the ionization to recombine and no longer be ionized. So it's no longer any use to us for sporadic E. So it tends to put a lower limit. The other thing is this descending node malarkey is a bit it's a bit like you know, when you hear talk of tidal surges around the coast and strong winds coming and you get a big storm, and if it coincides with a spring tide, you have problems with flooding around coastal regions. And one of the things in meteorology that we have to wrestle with situations like that is if the strong winds run ahead of the high tide. So in other words, these triggers, if you like, have got to come along in phase for it to be a peak event. And the same thing is true of this making sporadic E. The descending semi-diurnal tidal node here has to keep up with the ability and the distribution of meteor debris to keep working. What can sometimes happen is that it looks promising as it starts to form, and then this semi-diurnal tidal window, which is fixed really by the rotation of the Earth, so there's nothing we can do about that, that's going to keep on going, and that can run through the place where the stuff is converging, and you don't make a very good job of keeping that patch going. So in other words, you get a trigger, it's briefly coming through at the right time, and then one goes on ahead and leaves what's left behind, and it slowly decays. So that's one of the problems that we have. So I thought to myself, well, how can we get a little bit closer to this? And obviously, you've all seen these ionograms plotted. We have our local ones in this country in the form of Chiltern and Fairford, which is offline at the moment. But in amongst all this, there's one figure here, which is the critical frequency of the sporadic E layer, and there's the virtual height of the sporadic E. So there's two bits of information there that I thought might be worth looking at. So here's one bit there and the other bit down at the bottom there. So let's see what happens when you try and plot it. You could say, well, is it really important knowing what height it is? Well, it is kind of, because it tells us how much more time we've got left to converge the stuff. You know, if we're already down at the bottom here, where it's leveling out, then there's not much more ionization it can scoop up and bring to the party, so to speak. We've gathered everything up. So that is quite important to know that, but also just from a geometrical standpoint, you know, if you've got a layer at 140 kilometers of sporadic E and you've got one at 100 kilometers, there's, you know, about 400 kilometers of skip distance difference between those two. So in the world of these VHF and 50 meg contests, this is all very, very significant. So we got to, you know, be aware of what order these things are happening in and so on. So I experimented with trying to plot on a given day the change of the height of the E's against time. And to explain what this graph shows, the black line, it shows how noisy the trace of the height of sporadic E is. The intensity of it I've marked by this color shading in the background, where the intensity is enough to possibly be effective at 10 meters, and in this lime greeny color here and another one here at 6 meters. And these are bits of data based on the ionosonde readings. So you can see we can identify on a good example, they're not all this good, you can identify a descending phase going on with the height of the E's, and you can see some other stuff here as well. So it's not quite as simple as just two main things. This could be, it's not that one goes back. One of the things with this, combinations of gravity waves going on, interacting with each other, it can, what's happened there? There we go. It can complicate things to the point that you look at this and you think, oh, well, that means it's going back up and then coming down again. This isn't a patch of E's that goes down and then up and then down and then up and so on. What this is one zone descending and then another one forming higher up and coming down again, and so on. So we're getting a combination of different descending gravity wave signatures. Two main ones would probably be the semi-diurnal tides, which show up to a greater or lesser degree, but you also get other intermediate tides in here as well. So you know, just when you think you got something that reveals a bit of you know, a bit of clarity, shall we say, you find you haven't got as much. So I thought, well, let's do this by looking at the differences. So just as an example, I took the middle of the month for January, March, June and November. So we've got midwinter, traditionally not a sporadic E time of the year. We've got a very nice descending node here. There's one there in the morning, but that didn't seem to do much. But here's one in the afternoon, evening, and that seemed to have quite a good stab at producing something. And then March, it's a bit not much happening at all, really. It doesn't really seem to do very much. And it's impossible from just these isolated examples to draw big conclusions. But what I'm saying is that now I've got these programs written, it's going to be possible to keep on top of this, going through this event by event, and hopefully it'll reveal some clues. But you can see big differences in the effectiveness in June. Mind you, the wise amongst you are going to say, well, look here, chaps, we've got this really strong showing, and chapesses, this strong showing descending tidal node here, and hardly anything here, yet much better response of E's. And this is where we have to go back to this idea that schematic at the beginning with all those ellipses, you know, it's not just one thing we're looking at. And what I suspect we're going to find, or we would find if we looked at a different chart, would be this is when you have maximum input of background meteor debris. So it's like you've got more fuel to make the sporadic E with. So that's what determines the coloration and shape of this. Now, what will be revealed is, going through the season, do we really have weaker semi-diurnal tides in the summer than we do in the winter? What's going on here in November? That's quite a good response there. Is that the Leonids meteor shower? It's just fascinating when you can put these things out there and see things on a real-time basis, that you can start to make some comments on it. But the intermediate bits are just, I mean, February is pretty pants and September is not brilliant, although sometimes the sporadic E season does just struggle on into the middle of the month. So here we have a period in the upper atmosphere where these tidal descending nodes aren't particularly strong. I mean, there's evidence of something there and something there, but why is the E's bit not happening if you've got those components? And it may again point back towards towards the meteor input. So I thought that was fine for showing the height. Well, what about showing the intensity differently? And this is, just spend a moment or two getting your heads around this. So this is a color-coded time through the day. So it starts as blues and goes through greens, through yellows, reds, purples, greys, and so on. And they're plotted on this chart where you can see that the height of the E's is not constant, but you can get a drift of an idea. So in this period with the greens, you'd expect the greens to go into oranges and ambers colors, and here you can see stuff starting up at about 130, 140 kilometers, and then drifting down, and you can see hidden under here some orangey colors from the morning opening, and it gets to about here, about 5.5 megs FOEs. And then there's a separate one that starts also a little bit lower at about 120 kilometers, and that's a middle of the afternoon color, 1600, and that doesn't have far to travel before that tapers out and comes out here, but that gets much higher, and it gets to over 8 megs FOEs, and the time between here when that starts and when the last reading is all in this purple section, so it's about 3 or 4 hours. And then down at the bottom here, can you see just at the very lower edge there's some bluey colours, and this is early hours of the morning, and it gets masked by things later on and probably decays because it's lower down. You can see this is down at 90 kilometers, so it's in the denser part of the atmosphere and probably reabsorbed and so on, but that's what's left of a tidal a diurnal tidal marker probably, but this stuff here will go somewhere, so what's left of that will combine with a tidal one. So anyway, long and the short of it is that when you start plotting these, you reveal a lot more about E's than you hitherto get from just looking at who's worked who, although you need that. The fact is, if you can see what's going on here and know which bit of this cycle you're in, you'll know whether you're in a rapidly increasing frequency of E's here. Like this, it goes from 4 megs to 8 megs. It doubles in the space of about 2 or 3 hours. So operating wise, going for maximum bonus points in VHF NFDs and things, this is the point where you want to be really moving up the bands pretty quickly once you've established that it's got to here. Anyway, let's do the same thing for our different months, and you can see there are some. One of the striking things that came out of this when I started plotting it was how focused these E's are when you get good openings, and you'll see that this is the same scale here, 7, 8, 9 megahertz for FOEs. You'll see January and June are capable of producing the same FOEs. Well, that's something that I wouldn't have said to anybody before I started looking at this. So the only other thing that struck me about these two, I don't know if any of you have picked up on it yet, but if you look at it and sort of through what really stands out? What stands out to me is they're very similar in terms of focused for the height for the maximum E's. 2, they don't always mean that you get a better one in the afternoon than the evening, because here we've got one in the morning that's better and one in the evening that's better. And thirdly, look at the difference of what's going on here early on at low values of E's. It's pretty incoherent sort of stuff. That's fair. You wouldn't get much of a clue what was going to come out of this. Whereas this, it does sort of come up with two moments of possibly focusing, but it seems to be much more organized. Anyway, we move across here to March and November, and there's a lot more scatter in the lower values, and then November does at least come up with something, but as I showed you on the other type of plot, it may well have been this coincidence of picking the 15th of the month. Happens to be a Leonids meteor shower time, as I remember, so it may be we've lucked in and picked a time when there's plenty of coal in the bunker. But anyway, it just shows how interesting it can be when you start looking at things like this, and then you get this hugely scattered things, and then before you start thinking, well, this one's all right, look, it's going all right. We haven't even got to 4 megs here. The scale is different, so So this one in February, it struggles. It does have a bit of cohesion about it, but it's not very good. September is all over the shop. There's very little sort of, bearing in mind you're getting responses from all sorts of different heights at the same time. So yeah, right. So now I want to have a talk about what's on this lower map on the side here, which is something I've called an ease probability index. So this is a way of trying to combine all of the different weather parameters that I think might be able to generate these atmospheric gravity waves that go up and modulate these tides. So as a way of saying, you know, I'm not going to be able to sit here and write blogs on PropQuest forever and a day, but I'd like it to be a useful site that will continue to give people clues as to where it's all going. And this EPI index was a way of making it simple enough to try and understand what's going on a day-by-day basis. So originally we started out with radial rings, and roughly speaking, halfway between, you'd expect to see it crossing usually the edge of a jet stream between two stations having a QSO. So what is this EPI? Well, it's an index. It's nothing hugely scientific, other than a way of trying to factorize the things that might be involved. So it's a function of weather stuff, and it's in turn sort of operated on by, the unkind have called it a fudge factor, but I've called it a sort of a factor which kind of will accentuate some of the things which we know to be important at certain times or locations. We'll come on to these all individually in a moment. So this isn't about whether ease actually happens, it's about whether it happens where we think it will happen. So if it's going to happen, why do we think it might be here in these higher colours on the map? Not whether it could still not happen, but if it does happen, we'd like to think that this will eventually allow us to track down where. So these weather bits will give us a number between 0 and 100, say, and the other factors will be used to adjust it. It varies between 1, if you multiply it by 1 it stays the same, you're not doing anything, but 1.5 up or down, so it can suppress things or increase things depending on what else we think might be going on. So it'll never be more than 100, and we'll just see. I can put stuff in the programming codes, and we can have a tinker with things and just leave them set at 1 till I come up with a good idea. So the jet stream bit in the weather, these are the weather bits now. So the jet stream bit is scaled by the strength of the 300. In the old days we called them millibars, but now they're called hectopascals, same thing. So it's the height of the jet stream wind charts that we use in meteorology. So it's the strength of the jet stream basically comes in there. Vorticity, particularly on the edge of jets, is coming into it, and in fact it may even be more significant in the future. I'm doing a lot with vorticity at the moment. Changes of the pressure pattern, which was an attempt to get, remember what we're trying to do. We're trying to find out where we think there might be turbulence in the atmosphere that will generate this wave motion. So things spinning, you'd think, would be quite good at that. But if it's just spinning all of its own, it may not be as good as something that's spinning and moving. So moving things, like how quickly this upper wind pattern is moving, I've put in. Convection parameter, this is thunderstorms basically. This is like saying big thunderstorms have long been associated with sporadic E, but I'd have to say informally that over the many years, I started doing an article for Radcom in I think 1988 when Pat Hawker was writing technical topics, and he was the editor at the time for that particular type of article. And I remember driving down to Croydon in the middle of the night to drop this off for the deadline. That was in 1989 I think. So I've been trying to get my head around sporadic E and weather links ever since. So we're looking at 30 odd years and up, and throughout that time people still jab me in the shoulder at the conventions and say, look, it's all about thunderstorms. And to be honest, I've got to say, thunderstorms have been a disappointment to me. As a meteorologist, they're fantastic, but as Sporadic E contributors, they're not particularly good, I don't think. And the reason I say that is because mostly the thunderstorms we have are moving. You know, they're drifting with the mean flow in the middle of the atmosphere and they're moving. So they're not in one place for long enough to make this wave motion that's going to go up. And because it takes time, you've seen an hour or two to make an ease patch. Well, in a couple of hours, a thunderstorm can be 100 miles away, you know. So it doesn't turn out to be a particularly powerful component in that set of weather things at the bottom of the big schematic. What may, on the other hand, sometimes happen is that if you get these intense summer thunderstorms over the continent, say, where there's no wind flow, they're in a slack area of pressure changes, and the storm just is a massive torrent of activity, and sometimes there is an argument for saying that could have an impact, and they would be a different class of thunderstorms. For most of them that we're dealing with, they don't appear to be very important. Jet streams and vorticity associated with them are much more interesting. So this thing here, the stratospheric wind regime, what's that mean? Well, that's the bit that these gravity waves have to propagate through in order to go from the weather bit lower down to the ionosphere up above. So it follows what they go through does affect it some way, but I'm not quite clear yet how important that component is. But I will say that the mean stratospheric flow at 30 hectopascals or 30 millibars does have a flip over from a westerly in the winter to an easterly at about the seasonal differences for Sporadic E season. It's just, now that could be a correlation that's not there for the physical reason. It could just be how it happens. But it's certainly something that I've noticed subjectively over the period. The upper ridge is a bit like imagining if there's any turbulence and kerfuffle going on, like you see a sand dune that's growing in the wind. When the wind blows a sand dune, you've got all this overturning on the ridge, the crest of the sand dune. So if the atmosphere is doing that, there's probably turbulence. But anyway, that hasn't either come up with the big things. But let's have a look. So on upper air charts, this one on the left is the sort of jet stream map that my colleague at work, Dan, has developed for me to show where the jet streams are, but also one or two other things. Now, one of these things is, okay, the thunderstorms are these magenta orangey bits down here. The jet streams are the green shading, and the stronger jet stream core in the middle is an orangey yellow colour. And then I thought, well, I'll try and look for movement of the pattern. So we look for changes. These black lines on here are in effect the equivalent of isobars at upper air level heights. They're not, they're the height of a pressure surface, but just take it from me, think of them as isobars, and you can interpret them as being strong winds where the lines are close together, the black lines. But if the pattern's changing a lot, then we draw these blue lines denoting areas where the pattern is showing increasing values. So it's like a building ridge. And then red, this one in here, which is very similar to what's moving across southern Scandinavia and the Baltic today. The same thing that gave us our rain today has got an area like this, got into the black there. Anyway, so this is falling contours. So things where the atmosphere is in rapid change, in an atmospheric sense, rapid change is very important, potentially, I think. So that's something we're looking at. And then we drifted across to vorticity, and we started looking at that. And vorticity is really interesting because it's little ribbons and curls of the atmosphere. It's a bit like you've stirred coffee in cream into a coffee, and you're looking at little curlicues of cream going around in there. But it's areas of spin. It's a bit like when you see little vortices breaking off an oar when you're rowing your boat in the canal or whatever. Anyway, some of these things may be important. So these are all things that we're looking at. And then we have the factors, the adjustment factors. Well, time of day we've talked about, because that's the semi-diurnal tides. So we know that needs a little bit of a boost in the morning and again in the late afternoon and early evening. The seasonal factor, what do we mean by that? Well, we have this notion of a sporadic E season. I have tried to refine that a bit now. So instead of just taking months, I've kind of combined this factor with the meteor input, because if you look at the background meteor count, that has a seasonal variability, and we're trying to get some better results on that. And the RSGB has got a nice little meteor measurement project going on, a meteor radio beacon thing. So that'll be very interesting to see what results that gives us. So that will give us a time of day factor and a seasonal factor. Topography. Now, the landscape does interfere with how gusty the atmosphere is and how turbulent the flow can be. So that should be in there somewhere. So mountain ranges, I feel you kind of want to have in the deal. So places, regions where jet streams blow across a mountain wave, and a mountain range, you can set up standing waves over the mountain. So that could be really good, because these things interacting with mountains, the mountains aren't going anywhere. So this is a pattern which will give a good forcing that stays in one place for quite a long period of time. And then there's the dip angle of the Earth's magnetic field, which is what makes it all happen. You're blowing charged particles that go along the dip angle of the magnetic, so it's converging things down the magnetic field lines. And well, interestingly, that varies, of course, as you get away from the poles, and there's a magnetic equator, which you'll see on these EPI maps. And then there's how disturbed the Earth's magnetic field is, so the K index. And then there's I put in solar flux index, because there are times when that, I think, might have an input too, but not quite sure where and how and so on. But there have been times when that's figured. So the beauty of all this is that now this has been done, I've written a whole suite of Python programs to analyze these things. I can go off and get data sets and retrospectively compare them with my big data set that I've acquired of the ionoson data for the places I'm looking at. So we can get to the bottom of some of these things. So let's have a look at this particular example. A QSO here fits quite well. We're getting used to the idea of what colours represent what. The one thing that does come out is that you'll be amazed how often there are potentially good weather reasons for the you might say, well, you're obviously going to get this right. It's a bit like saying sunshine and showers. Whatever it does, you got it right. And this is a bit like that, but it just shows how many opportunities there are. And one of the interesting things about this is we don't yet know which ones of these are more important than the others, and it's data from people's logs and the ionosons that will allow us to get closer to that. So on this date, now remember, we're going down from the UK, from here in East Anglia, down into northeastern Spain area. So this is where we're going. And here you can see the actual ionoson data of the day. Isn't this fantastic? Oh, incidentally, this little blue thing here, which you can't read from where you're sitting, I would think, is I've had to convert these FOEs into something that means something in the amateur world. So taking what seems to work out as a subjective relationship, roughly the MUF, the FOEs, is a 10 times factor for FT8. So if you've got an FOEs of 10 megs, then that equates to 50 megs for FT8 digital modes. And if you've got an FOEs of 10 megs, then on sideband and so on, you've got an 8 times factor. So it's slightly different for the two modes. FT8 does add a lot of sort of activity to a thing, which makes it sometimes quite difficult to sort out the wood for the trees. But anyway, here, just see how this zone intensifies as it gets lower and gets all the way up to 4 meters. So that was quite good. Both modes got into 4 meter territory on that one. And here is now this is really striking, isn't it? You can see some very nice looking descending nodes here of the semi-diurnal tides, but there are several sort of hot spots where within that you've got little lesser descending bits, which also seem to have an ability to focus the ionization. So we haven't got to think of it as just one thing doing it and that's all you get. There's one thing doing it, but it's being modulated with other little bits that can give you hotspots as the trace comes down. So that and you see here that event got all the way up to an FOEs of 12 megs. So really really good. Anyway, so this I can press a button and run that, and it's instant. And if a day happens where there's an interesting path, I can just plug that one in, boom, press the button, and we get the graphs like this. And that's going to be tremendously useful for trying to get to find out what is the more significant patterns. I don't yet know enough about this to know what the pattern of these descending nodes has to look like in order to be significant. And it'll be interesting this year to see what these graphs reveal. So here's another one across the pond, and that shows a path between KA1 and HI8. So here you can see the midpoint on this particular path crosses the edge of a jet stream there, and that's possibly something to do with it. It's a maximum length sort of path, but still very interesting when you see these things nearly always hitting the edge of some tighter zone. Now the other thing about this is we talk about sporadic E paths and saying, well, how can it be that you can work all the way across the states? It's got to be so unlikely that all these things will fit in. But that's how the weather works, with a series of undulating troughs and ridges. So you're going to, on the right occasions, get several points where the intersection with the E region correlates with periods of enhanced probability. Don't know enough about these things yet. Are they all going to be the same length? Could we get an asymmetric sort of shape to the pattern? But it's a really interesting thing to be looking at. So the next thing was to do some of this verification stuff to see how close this is turning out to be. And in some cases it's okay. I've only just finished writing the software for this about a month and a half ago. So the first thing I've got to say in my defense is that we're now at the point where all the testing of the software has been done in the really pants part of the season, when you've got very weak systems going on and not really considered to be good sporadic E times of the year. So bear in mind, all of this is kind of the equivalent of grobbling about in the noise to try and find a signal. So this is for Roquette in northeast Spain for February. And along this top set of graphs, I've color-coded the background for the different band availabilities, if you like, depending on the FOEs. And the top lines here are where the FOEs has reached these thresholds. And then the bottom graph is where the predictions have been for the EPI index going into these different zones. So a 50% chance, a 75% chance, and so on. So some of them correlate really well. Some of them are busts. That one there is a bust, so that's interesting. This one here is a total bust on both graphs. So whatever we think might be doing it didn't do it, so that was good. But then you get some which did do it and had a very strong showing on the use. Now this is the first year that we've really been able to have a look at. I've really been able to have a look at the EPI. So this is the early. Now we're doing the adjusting and the testing, and hopefully not to make the magic smoke come out. So anyway, this one was a jet stream blowing down the chart. There's UK here near where the date is, and it's a northwesterly jet that becomes a northerly jet stream blowing across the Pyrenees here. So that gave a very strong signal from the probability index because of the jet stream and the mountain factor and so on, and it did produce a good response up to 6 meters, so that was good. Nothing happening in C, right in the middle of a big upper high, so no flow at all, nothing there generating the gravity waves, I suspect. And then this one which we missed, which produced good results and didn't get flagged up by the EPI, is in this sort of sort of zone here, which, well, I mean, it's ahead of an area of increasing jet stream intensity and rapidly changing contours. And I think this comes back to something which even only very recently, in the last couple of weeks, I've been talking to an ex-professor colleague of mine at Reading, and kind of thinking along the lines of vorticity and rate of change of vorticity as being important, and this one would fit the bill there pretty well. So lots of interesting things coming out of this, and say the one on the 1st of February, which we picked out, you can see there are several different components to this. You know, is it one descending node? Are there several different separate ones? Is this descending node steeper in the afternoon than the morning one, and so on? But not much data, of course, because we're in February. This isn't sporadic E time of the year, but it did get up to over 7 megs, so that was quite a good thing. But the color coding here, these purples, suggested that there was something here that seemed to happen at about 120, but it was kind of delivered earlier in the day, around the middle of the day, up here at a greater height, and then combined with what was coming in from here to make this slightly more intense thing. So there's your satellite picture, a sheet of cloud coming around the top of the jet stream up a ridge here, and then just stopping, dead halt over the Pyrenees, and nothing to the south of the Pyrenees. And then we had the one where we didn't get it, and this was again two rates of descent of the nodes. So I'm not quite sure. You can clearly see here there was a descending node which in a very short period of time produced a significant patch of ease, and stuff here that kind of fell apart a bit, didn't really get too coordinated, but did along here. So lots of interesting things. But this was a wind from the south, so there's something we need to have a look at there. Case C, when there was no wind, this was the big upper high, no reports of ease in here at all. Significant. There's one there, there was one there, and one there, and one there. Okay, I haven't written the software to separate the lines out, but you know what I mean. This is no activity, and we didn't get above 3 megs, which is kind of interesting. And there you can see the clear skies that you normally get with high pressure. Right, and then I tried to embarrass myself further by doing some scatter plots of these things. Okay, so you have to go through this in a way, given the opportunity we've now got with this data, is to see how close the EPI is. Higher values of EPI should be higher frequencies. Well, jury's out a bit there, but you know, it is going up a bit. But when we refine the EPI, hopefully this will produce a bit more. A couple of interesting things. This is the velocity of the jet stream flow. And you can see you can get good ease regardless of what value the jet stream is blowing at. So that kind of says already one thing that's quite handy. It doesn't have to be a strong jet stream to give you ease to say 6 meters. It could be way less than, you know, the jet stream flow. You could be very near the edge of a jet stream and still get the ease. So this points to this edge of jet stream thing. Now I've got something on the border here, so I can't see what the lower ones are. This is, I think this one was vorticity, was it? I can't see because my diagram is in the way. Let's go over to this side.
Yeah, yes, it was vorticity, Jim.
Yeah, vorticity. You know, vorticity, if it's spinning in a certain direction, it's called cyclonic, which means low pressure, and anticyclonic is high pressure. Doesn't seem to be much going on here that helps us at the moment from only a small number of reports. But the interesting thing is we can now keep this updated through the whole year and start to get some feedback on it. But the interesting thing is when you see things like this, and like with the wind direction of the jet stream, is this really saying wind directions from this quarter is significant for sporadic E and not in here? Or is this simply saying this is what the weather pattern was doing during that period and only producing wind speeds, wind directions in that quarter? So we have to get a big enough data set to be able to say much more. But this is just to say the sort of things we can do. Right, have I? Oh, that's been up. Right. So anyway, just for the hell of it, I thought I'd have a quick look at Roquette and see what. There it is, and the color coding here is the strength of the opening. So the colored dots. If you get the lime greens, it's 6 meters, and the red one is 4 meters. And there's a zone in here which is wind from between 220 and 240, which is coming from the mountains to the southwest of Roquette. So this seems to be collecting the more significant E's. There is some stuff in here which is coming from a generally mountainous area, but not so marked. And there's some higher ones in here which are coming from the Pyrenees. And then there's not much in here, this range of wind directions, coming from the adjacent Mediterranean. Is this real? Is this significant? May not be, but it's interesting. So that will be watched very closely. And of course, we can do that for other stations and see if there's any relationship there between the mountains. And it's almost certainly not going to be the height of the station where the ionosonde is. It's going to be to do with what the wind flow does in the vicinity. No particular pattern for whether we've got falling contours, rising contours, cyclonic vorticity, anticyclonic, but that might produce some different results as we go through the year. This will be interesting to see what a whole season looks like. The percentage of 10-meter openings compared to E's values less than 10 meters, how many 6 meters, and so on. And this was a way of seeing if the EPI was kind of useful. So when it's low, you'd expect to have more no E's than E's, and as you get higher, you'd expect that ratio to change a bit. It's only a month in the poor season, that's very noisy. I'm expecting that to embarrass me further as we go through this season. But anyway, it's a pressing of the button job now, so it'll be interesting to see what happens. And having a look at some later data that came in for March, a good clustering of probabilities here, which got above 50%, and it produced a signal up to 4 meters in there. So that was good. And then I've developed another program, which I won't bore you with now, but it's a way of looking at all of the weather parameters in the 24-hour period when we're looking at an E's event. So these green bars, just to say in the middle here, show the E's event, the FOEs, and it's related to the EPI, this blue line. And is it related to the jet stream? Maybe. It comes right at the end of the jet stream being above 60 knots, but we found out from the scatter plots the speed of the jet stream doesn't really matter, so that may be just coincidental. Is it something else going on up here, some of these other indices? And I'll be adding a new one in here in the next couple of weeks about changing vorticity and things. So lots going on, but just so you know, we're not dead in the water yet. There's a lot of work from a proper full season that will help to verify some of these things. And the important thing is that we keep verifying it, which means we keep getting reports put up on the clusters, we keep getting ionosonde data that we can compare it against, and if it goes wrong, then I'll be the first to come up and say, yeah, this is not working, we've got to look at something else. But the important point is we've now got the software and the various bits in place that will mean that this season we can make some really good progress at identifying some of these things. And just so you know, it's not all a fluke. This is today. I thought, well, rather than have special events, so this is today, early in the season, jet stream, powerful jet stream going just across the southeastern corner of the UK. This is Paul, MM0ZBH, who put up his logs here, and he worked down into Spain, which is this one at the bottom here, and the midpoint of that is right over a high point, and his path down into Hungary across here, this also is a high point. So it shows the usefulness of the system. It's not yet so reliable that you'd say, for example, why isn't there a path here, say to Corsica and Sardinia through the middle there? What makes that path work and that one work, but not one across here? So what's that all about? How can we fine tune the bits that are obviously to do with this jet stream here, which are important. And because there aren't many ionosons out there, you don't have a great sort of resolution of being able to track down the real nub of it. But hopefully we'll hit lucky and come close to refining a few more of these things. But anyway, so that's that. So it isn't all a fluke. Some of it is, but no, not today. So anyway, if you want to contact me, please feel free to do so. And as I said at the beginning, huge thank you to everybody who works stuff and sends a login, and also to the Lowell Digison network, who maintain a wonderful database over in the States of the ionoson data. And it means that I go in for PropQuest, and we go in and access the database, get the values out for the plots for the FOF2 graphs that we want, and it saves a lot of people piling in and grabbing the same stuff. It means it's always there, it's updated routinely. Every 10 minutes we'll go in and get the new ionoson values. To DX maps and all the many clusters. I mean, there's so many that are out there. You can't mention them all, but because I've shown images from Gabriel's site, DX maps is one that I use, but there are so many others. So if you do support those clusters, you're adding to propagation knowledge. And to Dan Holly, my chum at WeatherQuest, who did all the hard work coding the PropQuest website, and WeatherQuest for running it on their server. So brilliant. A lot of people behind this, but thank you very much for listening. I think you've all done very well. I saw nobody falling off their chairs.
Yeah, brilliant, Jim. Thank you very much indeed. That was absolutely fascinating, and I'm sure I'm not the only person in the room here who's got some questions to ask. But who wants to go first with Jim on?
If it's okay with you, can I stop sharing?
Yeah, so please. Yeah, we can see.
So I can see who I'm talking to.
Okay, who wants to go first? Who's got a question or a comment to make to Jim? Yes, Russell.
So, quick question really. Does Sporadic E only play a part in the sort of higher frequency propagations at 10 meters, 6 meters, 4, 2, etc., or can it work lower down the spectrum at 20 or 40 or somewhere down there?
Well, funnily enough, one of the things which prompted me to start the FOF2 graphs was the way our conditions on our Monday night Norfolk CW net varied on 80 meters from one week to the next. And some of the times when the FOF2 had crashed way below 3.5 megs, we were still getting really good signals. And that was from some Sporadic E, which showed up on the ionosons.
Okay.
So yeah, it's a spectrum of things, but ultimately you reach an upper frequency limit. So I think in the States you've got a band that goes above 2 meters. Was it 220?
Yeah. 220.
I think, but anyway, I can't honestly say whether I can remember whether 220 has recorded it, but up to 2 meters. But it gets less because you imagine you need more ionization to get the higher frequency going. So the number of times, it'll be interesting. That pie chart will show how common a 2 meter presence is compared to the other frequencies. And then the other thing again with doing stuff like that from ionosons is that you've got to get really, really lucky for the ionoson to be right underneath the peak of the E's patch.
Yeah.
So the chances are we're not capturing a full-on Sporadic E patch with these ionosons.
Okay, thank you. I mean, I was wondering, if you were sort of saying, okay, you get 10 meters but not 6 meters, would you also have to say you get 15 but not 10, or 20 but not 15?
Well, funnily enough, it can seem, well, I'll just put one other point out there. It can seem like that because simply as the ionization increases, the frequency bands that you're able to get will be higher, obviously. But the point is, as the ionization increases, the amount of bending of the signal in the E's layer will shorten the skip. So you will suddenly find you had an opening on 10 and then it disappears and you think, oh well, that's it, that's done. But if you'd have looked on 6, you'd have found it had gone on to 6 because so be wary of this thing that the the skip distance will decrease is a sign very often that the activity is intensifying, the ease patch is developing.
Okay, thank you.
Lovely, thank you, Russell. Anyone else with a question for Jim? If I don't see you straight away, then do shout. Yeah, Roger.
Hi, Jim. Just turn my volume up. Thanks very much. That was interesting. I wondered if anybody's done any practical experiments. You mentioned the seeding from the meteors. Has anybody tried to seed the atmosphere artificially, well, the upper atmosphere, just to be able to measure the effect of that and put some numbers on it, etc.?
Well, there is this Superdarn sort of experiment type stuff, isn't there, that's going on up in Alaska, where they're putting sending rockets up with some chemicals in that cause ionization, and they can track that. So they are, but it's an expensive matter getting things up to 120 kilometers, you know.
Yeah.
So in terms of sporadic E that we would deal with, nobody's been able to set up a practical experiment that you could do with amateur funding. One of the interesting things that happens though is not Superdarn, I mean HARP, don't I? I think the HARP experiment you see in Radcom now and again referred to, and the HAM-SCI people, there's a lot of folk there working that, and that's a very interesting project. Where they radiate a powerful signal up to energize a section of the ionosphere, and they can track how that behaves according to the stimulation of it. But the other thing I was going to say was all these GPS satellites that are up there now can in effect do what is known as limb sounding. We use it as a technique in weather as well, but you can communicate between one satellite and another and make various assessments of the point where you have a grazing incidence over the Earth's surface between the two satellites, and that allows you to build up a planetary sort of climatology, if you like, of ease intensity, and that's filled in a lot of gaps. And what's not clear when you do that is why a patch. It basically averages over, say, 30 years or 20 years or whatever length of time it is, where you're more likely to get ease. What it doesn't do is look at what I'm at, is looking at the individual daily events hour by hour and seeing what it is that makes that. Because the holy grail with this is, if it turns out to be to do with weather patterns generating sufficiently strong gravity waves, that makes them more likely to produce sporadic E up there than other areas, then because weather patterns, we're pretty good at forecasting the weather now. I think I've got away with that. But we are, and particularly for upper air stuff. And when you look at how aviation relies upon that sort of information for flight planning and so on, these things are really pretty reliable, these big mathematical models of the atmosphere. So if there can be linkages there, then it follows we could end up being at a point where we say, okay, next Thursday is worth looking at because of such and such a pattern, and so on. And that would be way better than saying, okay, I'll book that week off in early June because there's a big meteor shower then. It may get lucky some years, but it may not.
No, that's interesting. Thank you.
Gerald and then Terry, I think. Gerald, you're on mute.
Sorry for that. Forgot to turn it on. Right, yes, just wonder if there's ever a case where you get a combination of tropospheric and sporadic E working together to sort of get a further distance.
Yeah, that's a really good question, because there have been many investigations of those types of events, and I'm sure there will be. So, for example, you could imagine when you have transatlantic paths across to the Caribbean, or paths that are double hop into the Mediterranean. Tropo is almost a permanent feature in the Mediterranean over the sea there during the summer months. So there may well be points where you get a bit of that going on, but the point the point that I would make then is how you get the angles right for the second hop. But it has got to be, it's got to be possible in the sense that if you've got a multi-hop path where you've got these things, we draw them on bits of paper like this, but actually they're like this. They're so shallow that you can imagine at one end you could couple into a duct and get into some tropo stuff at one end of it. The really interesting thing is that sometimes you can't tell which it is just by listening to it. As a general rule, though, Sporadic E tends to be very flighty. Okay, there'll be a window when there's Sporadic E about, but you very rarely hear one signal for a very, very long time like you would on Tropo. So Sporadic E, the other trick test is to say Sporadic E will become less prevalent as you go up in frequency, whereas Tropo becomes more widespread as you go up in frequency. So if it's Tropo, you would expect to see something on 70 centimeters, say, if you're dealing in the European domain close to home. I don't know how you'd cope with that on an HF multi-hop path. You know, that would be interesting. But it's a good question to ask. You know, it is just too difficult to say because we don't measure enough of this stuff everywhere to be able to say. But there's no fundamental reason, I think, why it doesn't happen. I mean, you do get, I'll just say something else, you know, when you're working something by these exotic modes, whether it be Tropo or whatever, you do get sudden peaks in a signal where a signal comes up in amongst it all. Well, that's a combination of, say, Tropo and Meteor scatter, for example. So, or aircraft scatter. So there's all these things that there's no rule that says, oh no, I'm busy doing aircraft scatter, you can't come in here, you're blooming Tropo. So I would say, yeah, there's going to be, you know, there's going to be combos.
Okay, thank you. Something still to think about.
Yeah, it'd be nice if you can prove it. Yeah, get out there, get the logbooks filled up with some mixed mode things. That'd be good.
Terry.
Yes, hello Jim, greetings. Is there do you make use of the database, which I guess exists, generated by all the whisper signals that go on, WhisperNet and so on?
There's a huge amount of data. It's really good to see you, Terry. Terry and I worked together back at TV Centre back in the days, and yeah, Terry operated in the sanctuary at the end of the corridor when I used to work there. I always used to love going in there where all the radio amateurs were, and that was my hide-up zone. The whisper stuff is a bit like digital modes for me, Terry, to be honest, because when you're trying to, in the early stages of a investigation like this, I'm trying to focus on the things that are most important and giving the strongest signals. And the digital modes and probably the whisper, I have to say I haven't looked at that yet, but those databases are just so vast that when I'm trying to resolve whereabouts on a jet stream things are, it just gets totally swamped by data to the point where I haven't got the processing ability to deal with it all yet. But that may come, and when we get to phase 2 and I've proved to myself that these programs are working this year, then those big automated data sets would be really valuable, like the clusters and Whisper, and going direct to the raw sources, and not, because the thing is at the moment, the stuff that I'm looking at subjectively for saying, oh, that path's worth looking at, it's only if somebody happens to be in the shack on that day and has a QSO and logs it. It could be a good path if there was nobody in the shack and I didn't get to hear about it. Could still be a really good path. So Whisper is a good way of circumventing that little problem.
Yeah, and the reason that I mentioned Whisper is because so many people run Whisper beacons, both transmit and receive.
Exactly.
Paths will be discovered that humans wouldn't. To get rid of some of the vastness of the data set, you could set it so that only things which were sufficiently strong to make it possibly interesting to sideband or CW, that would whittle it down. So just set your signal level that you're interested
Yeah,
in.
that's an excellent step forward to phase 2. I think I've had a play with a raw feed from an FT8 log that a friend up here sent me, and managed to decode that, and that was quite interesting. But again, it's the irregularity of those individual logs that makes it difficult to come up with anything too wide reaching. But the Whisper thing and the clusters, the DX clusters, would be a logical next step. But at the moment, I'm still I'm still picking pieces up from the floor after having got this far with it. So that will be next year's development, Terry. But thank you for mentioning it, because I think that will have to come. I can't pretend they're not out there. We'll have to bite the bullet of the big data sets.
Yeah. Thank you.
Thank you, Terry. Anyone else with a question to Jim? Yes, go on, Robin.
Just a quick question. Something that I've noticed with ease, I on 6 and 4 meters. On 6 and 4 meters, I use just a dipole or dipoles, where I can switch between them and change polarity. And I've been very aware during ease how much difference there can be between the two. You know, you switch from one station to another, or switch the dipoles between on one station, and it can be a lot stronger on vertically polarization as opposed to others. You know, and is there any sort of data that shows that ease can actually shift polarization? And
yeah, well, it's good to see so many of the old guard on the on the chat this evening. This is fantastic, and thanks for the point in the 80 meter CC on the key the other day as well. I think you've got somebody very close to you, Robin, down there, who's Chris Deacon, IFX, has done a lot of work on polarization differences and using it as a way of detecting whether it's ease or not, and so on. Definitely have a check with Chris. He's done a lot of work with this diversity of reception, and he's written quite a few papers on it. So there's a lot of information out there.
I'll have a word. Thanks. Okay.
Yeah, he's the secretary of the RSGB's Propagation Studies Committee, but he's also top man at the UK 6 meter group, and he's done a lot of work, and he's currently doing a PhD at Bath University. So he's heavily into that type of thing. So you'll get all the information you need from Chris. It's very interesting stuff.
Okay, anyone else with a question to Jim? Jim, I've got one myself, and that is, I'm pretty sure there were people at one stage who were suggesting that there was a correlation between ease and the solar cycle. And there's an obvious reason why someone would suggest it, because the increased sunspots results in greater ionization. But it's pretty clear from what you were saying and the work that's been done that that is definitely not the case, because we get lots of ease when we're at the bottom of solar cycles, and we get ease right the way through the period of a solar cycle, and it doesn't seem therefore to bear any correlation to it. But I mean, you're kind of suggesting, as far as I can understand what you were saying tonight, that it's potentially a mixture of things, that the going through debris in the atmosphere, so meteors, is clearly one factor. Another factor are these very, very intense winds at that very high level of the atmosphere. And I mean, my question really is there potentially another factor relating to solar activity? I mean, just in the last couple of weeks, we've had these massive solar flares. We had one which, for a couple of hours, pretty well shut down any shortwave communication below 30 megs last week. One of our guys was on earlier tonight, one of our members, Tom, in South Africa, and he kind of emailed me saying, the bands have gone dead, Nick. I don't understand what's happened. You know, I need to go and check my cables, and then realised that there was this huge solar flare that had caused the problem. So, is there potentially another factor of solar activity feeding into it with the others?
Yeah, well, that's a really deep question, to be honest, because the essence of it is that the ionospheric physics side of it is not my particular zone. So I'm depending on reading and decoding stuff from others as to what's really going on up there. But the point that I think I have to say is that because I showed a schematic at the beginning, don't for 1 minute think that's all the items that should be on there. That was kind of how I needed to resolve it for myself, to see roughly where to start looking. The other thing is that there is, I'm almost certain in thinking there's a kind of an inverse correlation, that you tend to get better ease in the dips in the solar cycle than partly because the geomagnetic field is less disturbed. The thing about how this wind shear theory of Sporadic E is supposed to operate is that it's not so much speed of wind up there, it's the difference in direction. So if you think that you've got a charged particle, which is what this meteor debris is, and it's in the presence of the Earth's magnetic field, and it's being blown by a neutral wind that's caused by this semi-diurnal tide, possibly buffed up a bit by these weather-produced wind regimes, you can get a situation where you've got wind blowing one way above a layer of wind blowing in a different direction. And the fact that they're going in different directions means that one has a tendency, moving a charged particle through a magnetic field, it's you know, the old doodah rule, you're going to have a deflection, and the thing will be deflected in one direction if the wind is going that way, and in the other direction, so you can bring the two together. Now, that will work for as long as they're not dissipating. The ionization isn't being deionized, if you like. So there's some argument that would say, well, if you've got a stronger solar flux going on, there's more ionization coming in that could interact with it. You could also say that you're more likely to have flares and CMEs and stuff, solar disturbed patterns that will disrupt this steady state of affairs that gives stuff time to converge together. Because we've seen from those coloured dots on the graphs that it takes 2 or 3 hours to get its act together. So if you've got something that's changing a lot in a short space of time, it may not be enough. So all of this, cut long story short, is why I've put a new ellipse up there, which is the solar flux index, because we'll need to possibly have that in there somewhere. And it'll be for the people who work in ionospheric physics to come out with the reasons and what I really should be looking at. But the interesting thing is observations from amateurs. You can cross correlate those with the FOEs and see where we go. And if it turns out that the solar flux index is important, then that will have to get wrapped up in there. But you certainly can't ignore the solar input, because that will have an effect on, well, it has an effect on the height of these layers in the ionosphere anyway, because of the amount of energy getting into the upper parts of the atmosphere and solar absorption and changing strengths of upper winds that might be to do with the solar tides, semi-diurnal tides and things. So there's a whole bunch of things. It's all going to be connected some way. All I'm trying, I think, in my own mind's eye to do is to capture the most significant bits that relate to a position on a map that's based on weather stuff, because then those elements of it become forecastable. What I wouldn't be able to do, unless you plug in the stuff from the solar physics branches and NOAA's forecasting department and the Met offices who are now into that sort of thing, you need to plug in those things to come up with another factor that gives you statements about reliability of getting ease and so on.
So Jim, so the weather stuff is about, as you're describing it, the effect of the weather is not just that you've got strong winds, but they're moving at different heights, different altitudes.
Yeah, the weather,
and they're moving in opposite directions, and that's what's producing these clouds of ionized particles that we're bouncing our radio signals off, effectively.
Right, I'm gonna stop you there just briefly, because we've got to separate out the bit where the weather is at the bottom,
yeah,
which produces the turbulence. So that can have strong winds or light winds, and it could have spin in it. It could have all sorts of things. The air is always moving. The trouble is with the air, you know, we sit here and look out the window, and unless there's a cloud, which I can't see at the moment, you don't know what the air's doing. But it's got all this motion in it that's having an effect and generating turbulence and ripples and all the rest of it. These wave motions then go up to the E region. And it's the winds in opposite directions in the E region that are important. They don't start off in opposite directions low down and go up like that. It's stuff that goes up like that has the effect of getting winds and then printing a pattern on them that can make them appear to be coming from opposite directions. In the ideal case, usually it'll be slightly different directions, but it's often enough to get this convergent nature to the ionization. So where I'm at really is basically saying, if we can track down where the weather bits are that look to correlate best of all with where the E's turns out to be, is there a way of forecasting where E's might happen should everything else be right and all these other ellipses turn out okay? Is there a way of using that knowledge to say, here's a good direction for E's tomorrow and here's a good direction for E's on Friday? Without knowing the solar stuff at the top, you can't convert that into being there will be E's on Friday. There, you can't convert it into that because there are so many of these other things that aren't predictable on that time frame. But it'll come a bit closer to being able to say which are good days to do it and which are good days to cut the lawn.
I mean, what you've got to is another question for us, isn't it? We want to know when we can go on 10 meters or 6 meters or 2 meters and discover this amazing propagation that we're missing the rest of the time.
I mean, I say to people usually after these talks, I say, look, most people, there'll be some folk who haven't yet worked Sporadic E on the VHF bands. And all I can say is, if you do two things, you will work Sporadic E this season. I guarantee it. You will work Sporadic E. And the two things is be in the shack in the middle of the morning, and if you're not lucky enough to be retired and doing all that sort of business, then go in the shack when you get home from work before you have your tea and switch 6 meters on, and you will work Sporadic E. That evening period, if you do that every day in the E season, and it's a fairly broad season, but if you do it from the middle of May through to the middle of September, I guarantee you'll work E's on 6 somewhere.
Lovely, thank you, Jim. Right, has anyone else got a question to Jim before we pull the plug? Yes, go on, Terry, again.
Yeah, sorry, folks, I don't want to monopolise.
No, you're fine. Go ahead.
But amateur radio is what we do. This is absolutely professional level stuff. Of course it is, Jim. How many others in the professional fields, you've mentioned several fields, how many other people are investigating this sort of stuff and making use of what you do, and you making use of what they do? What's the size of the team, if you like?
Well, you never really know everybody who's working in this, but in most country there's somebody who's made Sporadic E their little bee in their bonnet that they're working on, and there is a group which some of you will be aware of and some of you won't, called HAMSCI, HAMSCI, and that's a group of amateurs. It was started up by an American group, but they had their inaugural meeting, I think, over here just before one of the RSGB conventions in Milton Keynes, and we had the day before the convention, and we had this group meeting of all people who work professionally in research, and some of these people who run these are folk who run the Arecibo, well, not now of course, but you know, they're people who run big installations and are doing proper deep space physics and at big universities in this country and in the States and so on, and they're so far ahead of the game in terms of all of this knowledge about the E region and things going on up there. I'm only tinkering around at the lower weather end, but in a sort of professional way. But there are people who work in a professional way in the research side in the ionosphere, and it's hugely important stuff to be across in terms of a lot of things, accuracy of GPS systems, you know, communications for share trading and all that. So there's a whole bunch of stuff which is affected by accurately timing signals and knowing what's going on along a signal path and so on. So I'm just trying to think of a phrase to use, but it is a topic of the moment in both professional and amateur research, and we won't all possibly know everybody else who's kind of dealing with it. But luckily, we amateurs, if you've got people who have a foot in both camps, and there'll be people over in the States who've got a foot in the professional ionospheric physics camp and in the amateur radio, in the same way that I've got a foot in meteorology and amateur radio, there'll be places where these things overlap and the information sort of leaks through the portal, and we can spread the knowledge around a bit farther. But there's huge amounts you can imagine that I wouldn't know at all about ionospheric physics. So I'm looking at it from below and thinking, oh, that's fascinating. I wonder if we can find out more about that. And there's people up there working on that side of it who are thinking, well, I wonder why that happens there and not there, and so on. And the whole thing about sporadic E research is, on a day when you get sporadic E, for me, why is it happening there and not just over there? Both places could have an equal strength jet stream. There could be many similarities, but there will be a reason why it's not in one place. And that's where this is, the journey's taken me. You know, it's we'll get there, perhaps.
Yeah, and I think a number of us have watched the fantastic videos of the space weather woman.
Oh yes, Tabitha.
Tamitha, yeah. I mean, that's absolutely fascinating.
Totally, and she presented, because I did this thing for the Hamsai workshop in March in the States. I did mine online, but she was there doing her piece this year. So she and I were on the same day together at that conference. So there's a lot of these overlap areas, and it's really ever so exciting that we can all sit in our shacks and operate in a hobby where elements of it are at the cutting edge of scientific sort of knowledge and experimentation. You know, it's what amateur radio is about, isn't it? If you're not building things and doing state-of-the-art stuff building, you can be propagating things and learning more about that. So it's just fantastic.
Okay, brilliant. Well, look, thank you very much indeed, Jim. That was really fascinating. And can we show our appreciation, everybody, in the normal way to Jim? Thanks very much.
Shout. Who's shouting at? Thanks very much, Jim. I'd let him have a diddle.
It's been a great joy being with you all. It seems like you're all a long way away, but you're not really. And these online meetings are just brilliant. So thanks for staying with it, and lovely to meet you all.
Brilliant. Thank you very much, Jim.
Thanks for running it,
Jim.
All the best, Jim.
All right. Cheers all.
Bye-bye.
Thanks.
Bye.
Bye. Bye.